Okay, we're live. Yeah, I can see, yes. Hi, everyone. Welcome to AUI Alumni Tech Talk series of webinars. My name is Ibtisam, and I will be the moderator for today's talk. So before starting, allow me to introduce the concept of AUI Alumni Tech Talks for those who are not familiar with it. So this series of webinars are organized by the School of Sciences and Engineering here in Al Akhawain University, and this is in collaboration with IEEE Women in Engineering and Arab Women in Computing. So they take place each other Friday, where we invite AUI alumni entrepreneurs, engineers, and researchers working in the tech field, of course. This is to share their experience with us and to discuss tech trending topics. So for today's webinar about big data and machine learning for industrial applications, we invited Dr. Bushra Boukhta. Dr. Bushra is an AUI alumna. She received a PhD in machine learning and artificial intelligence. And now she's a senior machine learning and AI scientist and program manager at Amazon Robotics Research, where she's leading programs in the area of automated intelligent systems to solve business problems for automated robotics. I hope I'm right. So I think she's really well placed to give us an overview of machine learning in industrial research and applications, and maybe walk us through a day in the life of a machine learning scientist. Thank you so much, Dr. Bushra, for accepting our invitation, and we really do appreciate having you here with us in spite of your busy schedule. Yeah.
Okay, the pleasure is mine, Ibtisam, and the AUI.
Just before we start, Ms. Bushra, I just would like to mention to our attendees that Dr. Bushra will deliver her talk, and then we shall open the Q&A session. I will not make you wait any longer. Dr. Bushra, the floor is yours.
Okay, thank you again, Ibtisam and Rita and Dr. Huda Shakiri, for the tremendous efforts for making this talk series reality, amazing event and amazing efforts. Thank you again for inviting me. The pleasure is mine. I always keep Al Akhawain and AUI very dear to my heart and close to my heart, so it's a pleasure for me to be part of this talk series today. And as Ibtisam mentioned today, so I will give you an overview a little bit about what it is like to be a machine learning scientist and AI scientist for industrial applications. And then I'll talk about two actually topics. I did a lot of research and worked on different products for AI and machine learning, but I picked two, one in robotics and the other one in renewable energy, specifically in wind. The reason I picked these two is not only because they're my research area and focus, but also because they are part of my, actually there are some new initiatives in Morocco right now. I was just in a meeting this Tuesday concerning celebration of women's international women's rights held by the Moroccan Foreign Affairs Ministry and the Moroccan, les Marocains résidents à l'étranger. And they really talked about some initiatives, especially in bringing machine learning, AI, digitization, and robotics, introducing robotics applications in Morocco, and really trying to be pioneer and leader in renewable energy. So that's why I picked these two areas. I think they're very hot topics, and I believe AUI can make also big strand in these areas, and we're doing a lot of collaborations with that regard. Okay, so let me start first by actually, so as I mentioned, I'll give a brief overview of machine learning and then really walk you through some of kind of like what it is to be a machine learning scientist, and then the two applications. I'll start with the wind operations and maintenance. So this is in renewable energy, specifically to wind, and then robotics manipulation in Amazon warehouses, actually. So what does machine learning mean? So people usually, they learn from experience. And we have traditional actually algorithms that are more programmatic, that actually use, let me actually go into slide mode show, and let's see, yes, this is better. So, and actually they follow instructions. So basically you build like what is called like rule-based systems. So these are if then else statements. You put if this happens, then do this, and so on and so forth, right? And robots, really, in robotics and machine learning in particular, it's really trying to help mimic the experience that how people learn from experience. And really, the robots, they don't really learn from experience. I mean, to some extent is experience, but it's really from data. And Arthur Samuel, who's one of the pioneers of AI research, he called it the field of study that gives computers the ability to learn without being explicitly programmed. So that's kind of like in a nutshell what AI and machine learning is, or the concept behind AI and machine learning. And then there is this concept of data science, which is really, you have machine learning, but there's this field that everyone talks about, and it's called data science. And actually, it's the intersection of multiple disciplines into one. So you have computer science, and you have mathematics and domain expertise. But more specifically, you need people who understand also data pre-processing. Understanding the domain is very important. And mathematics helps from the statistical aspect, but also machine learning has a big foundation also in mathematics. That's really what constitutes what's now called data science. So it's really, and if you look at Wikipedia description, it says it's a multidisciplinary field that uses scientific methods, processes, algorithms, and systems to extract knowledge and insights from structured and unstructured data. And in my talk, I will talk about a little bit about what means structured data and unstructured data at a high level, because in the application it's very important. So an example of structured data, you might have, let's say, temperature sensors that are positioned in different parts of the wind turbine, for example, inside of the nozzle and in the hub. And the readings, that data, it's called structured because it's very specific information and data that is actually, it's called tabular data that is stored, and you have a label for it. It's called the temperature in this case. Unstructured data, it's actually like a good example for unstructured data is images. Images, especially if they're not labeled, they're very unstructured, and you have to add a little bit more information or annotations to get a little bit more structure into it, so that you can provide these algorithms and insights so that they can learn and model that. All right, so really the focus is, if you see about it, really what's making this whole innovation is really machine learning. It's really at the heart of all of that. There's actually another concept, and I think I don't have it in this slide. So actually machine learning is part of something called bigger, which is artificial intelligence. And artificial intelligence, think of it as a superset. And within machine learning also, there is a new technology. Now it's very hot. Wouldn't say like that new anymore, but in the last few years, it's been like extremely useful, which is deep learning. So deep learning is a subset of machine learning, and also and I'll talk one of the applications, especially in robotics, using deep learning a lot. Okay, so now let me move into the next step, which is how, like as data scientist, as a machine learning expert, what's the process? How do I walk through solving the problem, right? So first, you have to have a problem to work on. So in an application, let's say, for example, in a wind turbine, and I'll give more details. In a wind turbine, you might have a problem of identifying when failures happen for maintenance and predict when the failure might happen. So that's kind of like high-level definition of problem. But then you have to dive into it and understand really the problem. So when you try to understand the problem, there are different pieces. So you need to identify what is the goal. Like in this case, you have a goal, which is identify when a failure will happen. You need to have actually a team. When you define that, you say, okay, so yes, I'm the machine learning scientist. I can bring that in, but is it enough? No, it has to be a team. So you need to have people who are engineers, mechanical engineers, people who understand the mechanics in this case, because it's an industrial machine, and then also people who understand like meteorology, because it's related to wind, and it's a very diverse team of expertise. And then you have also the operators, people who are really operating these turbines and really have them as part of that team. Just to name few things, right? And then you have to have a target. So for example, like, okay, so the goal is to identify failures. Can I identify all the failures? Probably not, because some of the failures, we don't understand them. So we have to say, okay, we will dissect the type of failures that we can identify, and how early do we need to identify those failures? Do I need to identify them 3 weeks in advance? Is that enough? Do I need to identify them 3 months in advance or 6 months? Right. So so that ties a little bit the goal with the target. And then we have to set up like, okay, so to solve this problem needs to be solved in a timely fashion. Otherwise, it's not going to be useful, right? I mean, you cannot just, there are some problems that are open-ended problems, but when you work in industrial research, you still have to have, sometimes you have to have a solution within 6 months, sometimes you have to have a solution within a year. And if it's really very hard problem, it can take several years. But then you have to set up timeline, even with those, like every 6 months, what you're going to be delivering, what is the small part of the problem you're going to be solving or researching and investigating, and then go to 1 year and so on. But most of all of that is having fun, because this is like, I call it like the job of a data scientist and a machine learning scientist is like an investigator and going in an adventure and fun, because you have your goals, you have your targets, you have your hypothesis. But as you dig through the data and then you use these algorithms, you don't know what you come up with. And I'll give some examples during some of the applications. So it's a really fun job to have. And the nice thing also, the problem, and I was very particular here to keep it very abstract, the problem, some problems or some areas, they become very hot, very based on the technology. But one thing that is always good and rides all the waves is machine learning. So you can apply it for all the applications. So which is extremely nice. I had that as when I was a student. I really loved math, and I really wanted to make sure that as part of being a computer scientist, like I bring the element of math, and really machine learning and AI spoke to me, because it was really kind of like that intersection. And also when I was a kid, I really always was fascinated by science fiction and pushing the limits of what could be, like the world we live in. So that's why I really wanted to do research, but also really wanted to push that AI aspect, because like robots, like what robots that are not robots that can destroy, but robots that can help, right? And maybe teleportation, all these things that are science fiction, actually, they drive a lot of the interesting things in science and research. So that's why like this is really, really exciting area for research, and it's going to be like that for a long time. So now let's look at the process. Okay, so we identified the problem, understand it. Now the first thing is really identify what are the data we need. So you put your hypothesis and all that, and you say, okay, where's the data I need? Is there data, right? And in this case, the data is all around us. But when you talk about industrial applications like machines, you really want to understand whether the data you need is there. Did they capture it enough at the right granularity, or is it like too high level? Like I call it the curse of averages. Don't give me average. If you can only record data every 10 minutes, don't send me a 10 minutes average, because data can be skewed. Please give me 10 minutes instances so I can look overall what's the trend. So those are very important. And one thing I am a big fan of, and also I really work a lot, very hard, is to educate the team of, as a data scientist, as a machine learning scientist, as an AI scientist, just don't throw the data at me and give me a problem. Say, okay, go work on your lab in your room and give me a solution. No, I really need to really understand what's the data, how it was collected, and give feedback early on to make sure that the data is collected, I can use it. Otherwise, it's useless, right? And I'll give an example later on. Actually, maybe I'll give it now because it's important here. So one application I was working on for wind turbines and identifying failures for gearboxes in a wind turbine. And the data that they sent us, and they said, oh, we have like plenty of data. We have 3 years worth of data from 6,000 turbines. You should be like in heaven. And these are like data, like we take 10 minutes averages. First of all, I was like, oh my God. At first, the averages. And then when I looked at the data, this data, it's all over the place, because, and then when I went and looked at how these sensors, these are vibration sensor data. Vibration sensors, they should be positioned so that you can pick up vibrations that are anomalous vibrations. But these sensors, they were placed too close to the gearbox. The gearbox is like a big house. It's like huge, and it rotates, right? It has lots of rotating parts, and every time it rotates, it vibrates. So inherently, it vibrates. So all the data we have was not really good indicator. So after a lot of discussions with the team, the hardware team, in the next generations of wind turbines, they started including machine learning scientists and data scientists as part of the discussion of where to place these sensors so that we can get exact measurements. Think of them as you go to a doctor and say, well, I think I have a fever, but I measured my foot. Okay. All right, maybe it's important, but maybe it's not. Or I put actually the thermometer on my shoe, and my shoe is outside, and it's telling me it's very hot. So I must have something. Well, it's not, because it's not really measuring your body. It's maybe measuring the temperature outside, right? So those are important things. So giving them this feedback and really engaging early on really helped in the next generation for identifying failures, as an example. The other thing, so let's say they give the data, you have to check whether the data is missing, because sometimes these sensors, they might be faulty, they might need to be calibrated. Some numbers might be read wrong, like if you're expecting a temperature sensor and then you have like 1,000 Celsius, it doesn't make sense because we're not in a furnace, right? So all these things, there is like making sure that you look at the data and understand which one is really going to help you. And it's a lot of data. The good news now is that we are collecting a lot of data. That's why there's this big push for big data. There's everywhere, but not all of the data is good. So you have to really, as a data scientist, detective, that's part of the job, right? And then the fun part starts, right? So you have to start identifying what are the models that would work in this case, right? And for that, again, as a data scientist, we have a lot of machine learning algorithms that we can use. We have to create new ones. But again, because some of these problems, if they're industrial problems, there is a very good foundation also what is called physics-based models, and understanding what those physics-based, because another challenge with machine learning and with data, you can find correlation with a lot of things. So you want to make sure that what you're finding is actually significant, statistically significant within the domain you have. And that's why mathematical modeling and thinking, it's not like really out of that, it's part of that, right? So, and of course, getting like databases and all that, that's important. So, but it's really how do you pull from all these different pieces so that you can build a model that actually extracts the right knowledge from the data you have at hand. So either to do predictions or to generate classifications or things like that. And then, okay, so now we talked about, we have the data, it's good. Now we need to analyze the data, right? So you start analyzing, looking and seeing, I need to see if I see trends, do I see patterns? And there are some tools, and I'll talk about this a little bit more. There are some techniques to do that in an automated way. Before, it used to be a very heavily manual process for machine learning scientists to do this work, and it's tedious and it takes a long time. But there are some really cool advantages now with the new technologies and a lot of automation, and I call it ML for ML, machine learning for machine learning, actually. Okay, so now let's say we looked at the trends, and now we try to check. We have hypotheses. Okay, so we say, okay, so maybe, because at the end it's not identifying failures, but it's really identifying failures and trying to solving them. It's not good enough to tell me, oh, it's going to fail in 3 months. Okay, why is it going to fail? And what is the part of the turbine that I need to change or fix? Or maybe operate it differently so that I can prevent that failure from happening. So those are hypotheses, and it's really, you have a lot of like you make a lot of hypotheses, and you look at your data, and you go and validate your data and try to extract what really from your models makes sense. Again, if it's a physics-based model that can tell you, well, you're seeing trends, but really from a physics perspective, it's not possible because, these two mechanical pieces, they rotate, but they are related to each other, right? An example, and I'll talk about an example later on when I talk specifically on the wind turbine problem. Okay, so now I described at a high level what is the process, and I talked about this concept of machine learning for machine learning, ML for ML, and automation. So as part of, there are lots of companies who have invested a lot in really providing a platform for machine learning scientists and applications in machine learning so that you can do it at large scale. We don't have an infinite number of machine learning scientists. They're actually very scarce. So this is a really good area for career. It's like really, really nice. I mean, it's tough, but it's really good. And you'll get like a lot of job offerings, even if you have, if you're really like in really good big companies. There's always demand outside of companies, inside of companies, because it's really niche skill set. But in order to amplify that, there are this concept of, so for example, Amazon Web Services, they have something called Amazon SageMaker. That's really a platform to automate some of these processes for machine learning scientists so that they can, for example, they can prepare their data, right? So connect to multiple databases, do some of that digging, do some of the data preprocessing, building models, testing the models, deploying the models, and then fine-tuning the models on the fly, or when the models are deployed into the field, and then really helping to make decisions at the end. And even the decision making is automated. So here, the data preparation, and I'm gonna dive a little bit more in each one of these. So the data preparation, you need to clean your data, you need to deal with missing data. Sometimes you have a lot of data, but you have some missing information because the sensors were down, or the connection was not good, and some of the data was dropped, or it got corrupted. And for that, there are some techniques where you can extrapolate to fill in some of those missing data. I'm not going to go into a lot of detail into those things. And if people are interested, I can answer some of those during the Q&A. And then there are ways, as I said, you have to explore your data. So there are massive actually algorithms and platforms actually to allow you to look at especially multi-dimensional, like high-dimensional data that's very hard to see and gives you like some insights, like there are heat maps and things like that if you go beyond three dimension of three features. And the other important thing is that this is how, as machine learning scientists, we say, oh, these are the features, these are the data that really will help me and solve this problem or answer this question, right? So that's, and sometimes the data you have does not give you the insight. You have to merge two, and it's called feature engineering. You have to merge two data sets or two data points, and then create something new, because it gives you another insight. The other piece, which is, okay, so you have your data now, you pick a model, there are multiple models you can do, and actually this is, there's a concept now called model ensemble. So machine learning scientists, they have to look at different types of algorithms and decide which one is good, and go through this process of dividing your data into training, testing, and validation, and then you basically what it is, you just pick a model. It's like y equal ax plus b, or in this case is w x plus b, and it's actually a function. It's more complex, but you're trying to estimate what's the values of w and b. So if you're talking about neural networks, it's actually more complex, because there are some processes to do that. Just to simplify it, that's at a high level what it is. And really, with the model ensemble, breakthrough, what happened is that you don't have to stick to one model, like let's say neural network or a decision tree or a random forest, or there are multiple different algorithms. You can pick an ensemble of these models, and then you kind of like let them work together and give you the best answer, because every model is good at in some cases, but they're not as good in other cases. And And actually what they do, when you pick a model ensemble, excuse me, what you do is actually helps you to pick the best, get the best of all the models, and diminish whatever is the disadvantages of those models. Okay. And then there is a concept of model deployment. In this case, so you have the application, you tested your model, you trained them, they're good. So you need to deploy them so that they are part of the software application, so that they're automatically excuse me, invoked to answer the questions over and over. And in most cases, it's not only one model. You have a pipeline of different models that actually the input of one model goes to a model, and then that model provides an output that actually could be part of an input for another model, and so on. And then last but not least, so you have these models provide you some insights or give you an answer to a specific solution question. So for example, like when will I have a failure? When is the failure happening? But really, what's the action I need to make, right? As I said, well, in this case, do I really need to change a part? Do I need to operate the turbine differently in this case? So these are called recommendation systems, and these are decision-making systems that take all of that, plus they rely on something called the knowledge base, which is knowledge either from the experts or overall, when there are good cases of how some of these things got resolved, it stores them and learn over time and extracts this knowledge base. And that's one of the things that it provides to the action recommendation system. So think of it as actually a good example is that IBM Watson, they have this recommendation system for doctors to give prescriptions, basically. So it's like augmenting doctors. And there are other examples, like when I was with GE, there are recommendation systems to provide when a failure is detected or predicted to happen. There is a recommendation system that goes out to the operators in the field and the engineers in the field and technicians so that they can go and check things and then do specific manipulations for maintenance. So this gives them actually what to do. In this case, you can get it by not using someone who's very expert to do everything. So you can have someone who's less expert, and you have this expert system on top that can help guide them. So this is really extremely powerful. Okay, so with that, I'll move into some of the industrial applications. I talked about wind turbines quite a bit, so I'll go through that quickly. But I just wanted to give you perspective of actually the wind turbines history. So wind turbines, they started generating. These are megawatts. So in 2005, they came up with the research for megawatts turbines. And now they have actually the megawatts. Now they're getting closer to the 13, 15 megawatts. These are huge towers. Now, do we need all of these? Do you need a huge tower, or it's better to have, like, let's say 100 of the 7 megawatt turbines or 1.5 megawatt turbine? Actually, in some cases they go for lower, but then a lot of them, because these tall wind turbines, again, maintenance for them, the area where they can be and all that is more expensive. These ones, they're relatively smaller. They can fit in different places, but you can have a farm of them. Actually, in Morocco, there are several wind farms. Actually, in the north, if you go through the Rif Mountains, you can see them like perched on the mountains, and there's a lot of wind there. And they're usually between the 1.6, I believe, and 2 megawatt turbines, because they cannot have them like very high, especially at higher altitude. So, okay. So, and here is kind of like at a high level, I already described what's like the failure mode problem. And it's really, again, like before using really machine learning and all of like the AI approaches, it was really mostly reactive. Like they look at this turbine, like these sensors, for example, temperature sensor or this vibration sensors, and they set up thresholds. If it is higher than a specific threshold, they say, oh, there must be failure. But it's really reactive, because if the vibration already is high, that means the problem already is there. And the failure actually happens within sometimes hours or a day or two, right? So it doesn't allow for, and just to give a perspective, these gearboxes, they're like the engine of a car, but they're the engine inside of the turbine that actually translates the rotating energy from the blades coming from wind, because the wind rotates the blades. It translates that into electricity. Basically, that's the transformer that transforms that energy into electricity. So these are very complex, huge machines. But if they break, it's called a catastrophic failure. The worst case scenario is that they have to replace that gearbox. And to replace it, they have to have very special cranes. They have to have very specialized technicians who can climb up these towers. Most of these technicians, they're usually rock climbers. Like that's the type of people you need. Plus, they're really good at what they're doing. And the operations, right, it's like about $1 million, $1.5 million, $1 million just to replace that. And the other problem they have is that these gearboxes, they're huge. They don't have them in an inventory sitting in the wind farm. They have them somewhere. Sometimes there is a backlog of orders, so they have to order. So sometimes the wind turbine might stay still without use for 6 months. That's a lot of money lost, right? So really, with the machine learning, was really to push it to be more predictive by actually identifying a node failure, but we don't know when it happens. But then using machine learning techniques to identify early on And it's not looking at maybe all the temperature sensors and all the other sensors, everything is under control. It does not cross any threshold. And that's called a univariant analysis, like one variable at a time, you look at it. But machine learning, it's multivariant, which means it looks at multiple variables at a time and really creates, models this complex relationship between them that identifies a failure. So everything might seem the same, everything is good, but then when you combine things, then you see that there's something happening, right? And then really what is nice, what's really important is that you try to predict failures that you didn't even know, you don't have data about it. And that's being proactive and extending the life. There's something called extending the life of these assets, of these turbines. So a good example actually using machine learning was there was a site, a couple of wind farms that had catastrophic failure. Only half of the wind turbines had this catastrophic failure, and they could not. There was no sign beforehand, nothing to define what happens. Like everything was fine, and then suddenly there is inside of these gearboxes there are like these huge gears, and each gear has a small tooth, and the tooth broke. And when it breaks, that's it. I mean, you have to replace the gearbox. It's not like something you can fix. So. And that was huge. So we did an analysis and we looked at everything, and everything seemed fine. Like we couldn't find anything. So one thing, and this is why the detective part is interesting, and building a team and trying to think about the problem from a system level is important. So I was like, well, you know, I know we're focused on the gearbox and we're getting all the data from the gearbox. Let's just broaden and let's look at all the data we can have from that wind farm. It's not only for that turbine, all the wind farm, the wind conditions, anything. So we got even reports on when they stopped the turbines, they started them, everything. And we did a really very, very good analysis, and we used random forests. And it was very interesting. We had found that actually there was something called an Estop. So Estop is the operators, the manager of the farm. They can stop turbines, and when they stop them, they actually literally push some buttons, and it's just what it does. It just puts a brake on the gearbox. It's like putting a brake on your on your car when you're going fast and you brake hard. That's what it does. And we realized that the turbines that had that, they had very repetitive breaks like that. And we tried to understand why was that? Like, what was that correlation? We found that. And we asked, what's the question, why? One of the answers we got was actually, so the wind energy is a very interesting energy. It's not steady energy. You don't get production of energy on demand. It's not like gas turbines. Gas turbines, you want more energy, you want more electricity generated, you put more oil or you put more gas. In the case of oil or steam turbines, you put more gas and then you get it. In the case of wind turbines, it depends on the wind, right? Sometimes the wind blows, sometimes the wind don't blow, or doesn't blow at the rate you need it, so you might not generate, or it blows in the direction that is, even though the direction, a lot of these turbines, they became very sophisticated. They have this nacelle that rotates, the blades also rotate and pitch to follow the direction of the wind. But still, sometimes you don't get high winds. So what they do, the grid usually puts to this energy producers, tells them, well, I need so many megawatts. Let's say, for example, I need 200 megawatts for tomorrow. And they do this bids. This very interesting, it's like a stock market thing. It's another fascinating thing where actually we use machine learning to do that, to do bids and also understand what is the demand, but I'm not going to cover that here. So when they do that, when they ask, for example, to bid, and the grid says, I need 200 megawatts, and let's say this is a farm of 100, just to keep the math simple, 100 turbines, each turbine can produce 2 megawatts, okay? So we say, okay, we can cover that, we're gonna bid on it. And and then let's say because the grid asks others to provide that as well, and then the bid comes back and says, well, yes, I know I asked from you 200 megawatts, but I'm reducing it because I got super production from this gas turbine plant, and now I need only 100. So which means I need from those 100 those 100 turbines, half of them I have to stop them. Because because the other challenge now, there is no really good way to store this type of energy in very efficient batteries, right? So that's another problem. I worked on it, but I will not cover it here. So what they do, so then the grid says, okay, I can only take 100. So what the operators do, they basically start breaking the turbines and stop them so that they don't rotate. And what they did with these ones, these operators happen to have their favorite turbines to always go and break. It's just by random, and it turned out that those are the ones that they break every time. Those are the ones that most of them had a specific, and we did another genealogy understanding of where the gearbox was manufactured and all that stuff. And we found that there was a correlation between these turbines being repeatedly breaking, and a defect, but it's a very small defect. It's like micro pitting in one of the gear teeth. And this is huge, a huge like gearbox, like very micro, like you can, it's like the size, less than the size of a hair, basically. But what was interesting is that breaking, what it does, it shakes the gearbox. Imagine when you're driving your car very high speed and you brake, your car shakes a little bit. The engine shakes, the whole car shakes. So these gearboxes, they shake and they shake. And every time, so that actually created a hair in that micro pitting, and basically the gear tooth broke. So long story short, so really for what was the recommendation we provided is that now if we understand this type of genealogy problem or defect exists in some of these gearboxes, the operations here should be different. So for example, like the ones that were healthy good, so we came up with the healthy index. If everything is fine and they're good, you can break them, you can do whatever you want with them. But these ones that have higher probability of failure, with this type of failure, you should not break them. You should just let them running. Just use the other ones. So that was very insightful and really, really saved a lot of money. Actually, about like more than $200 million for our customer. Okay, so, and just to give a perspective of from these machines, and I just talked about wind turbines, there's a lot of data that flows. So that's the other piece of the puzzle here, is that there's a lot of data to go through. So that's the big data problem. So if we think about wind turbines, so just each wind turbine, it generates like just wind turbines, they generate about 25 terabytes per day of data. If we compare it to, for example, Twitter, 5 terabytes a day. So it's really much more. And these are just wind turbines. We're not talking about other machines. This is like really huge problem. And there are about 300,000 turbines in the world right now and counting, right? So this is just wind turbines, okay? But it has thousands of sensors. You can think about all the other ones. Okay, I'm gonna go quickly on these because I think we're kind of like tight on time a little bit. So let me just move quickly on that. Okay, so now I wanted to cover a little bit robotics and the fun with robotics. So that's the next stage I am in right now. So robots, they're fun. They come in different sizes and shapes. And particularly in Amazon, the robots that I've been working on are robots for warehouse manipulations. So I know there's Amazon in Morocco that delivers, which is great. So I was very excited. I saw, I think like 2019, I came for a conference, Arab Women in Computing in Morocco, in Rabat. And then I saw, I believe in, I forgot what's the name of there was a new mall that was built, and then I saw Amazon. I was like, oh, Amazon here. So I started looking, at now Amazon is in Morocco, which is great. But just let me tell you a little bit about what goes behind the scenes. It's like this So Amazon has warehouses where, for example, sellers, they send their products to be sold on Amazon, and they have to be stowed. It's called stowed, which is put in place so that they can be picked up and then put in boxes and then shipped, right? And I can, and actually these warehouses, they're like the size of, well, the example they give is a football field, like 6 football fields, which is soccer fields, like similar. Let's just simplify things. So like 6 soccer fields. This is just, like horizontally. And they go up, right? So some of them, they are 2 floors, and they have an army of people working on them. But in order to guarantee that, let's say I order something and I click order and it tells me how long it's going to take. So there are a lot of algorithms in the cloud that as I am shopping and I am looking at all of these things, it starts already identifying based on my address where the closest warehouse is for that product, where it is, and then start actually having an algorithm that start identifying and giving commands for things to be moved around. And it has to guarantee. So there is something called Amazon Prime. I don't know if it's available in Morocco. So Amazon Prime guarantees delivery of items in 2 days. And they're pushing the envelope to have it in 1 day. So basically order, whatever you order, you get it guaranteed within 2 days window or 1 day, right? And that's huge. In the US, it's a country, but it's like a continent that is bigger. Think of it as much bigger than Europe. It's huge. Like you can order something that's in Seattle, and then you get it. I live in Boston, so I get it in Boston in 2 days, 1 day. That's amazing. So really, to do that fast, humans are obviously a big part of that, but robots came to the rescue. So these robots here to the right, these are the one of the robots that are used to actually carry what they call pods and ASINs, where items are, so that they can move them around and deliver them to humans to either pack or put. And then they also have something called, let me see here. They can stow things in them, so that it's called like a pod, and then you have different items are stowed in them. And then when the customer orders something, the robot brings the items in the shelf. It's actually a shelf. Brings it to the operator to just pick and then puts in a conveyor belt to go again to be assembled with the other things that you order, so that they can go into package. So I'm not going to talk about that today. I'm just going to talk about actually something that is actually even newer, because this is a little bit, it's new technology. It's good technology, but it's there's something called more interesting now. It's called robotic arm manipulation. So here are these robots that actually pick. So these robots. There are 2 types of warehouses. One warehouse where you have actually items that are stored like in shelves, but they're called pods in shelves. And so you're at the item level. And here they get packaged into boxes, and then they go into a distribution center. So this is like a sortation center. That sortation center gathers boxes from different places, and then they have to dispatch them to be delivered to the customer. And that's another very hard problem, because these boxes, they have labels on them that they have to go. It's very complex. They have to go through these chutes that go based on the area, the zip code and the area, so that they can go into trucks to be delivered, or into airplanes actually to be delivered. So in this case, so we have usually people. There are people, but it's very hard to keep demand. Sometimes, like the demand, especially last year and this year with the COVID. People have asked and have ordered lots of things from Amazon. It went like through the roof. So really to keep up with the demand and really help, especially like we had to reorganize and make sure that important things like are first served, and then other things, right? Like, for example, like hand sanitizers, masks, groceries, and things like that, right? But even with that, it's like the demand was huge. So we have this robotic arm manipulation is basically a robot that picks a package and puts it on a robot. So robot to robot manipulation. It might seem like very simple problem because, oh, the robot just have to pick an item and then put it. It's actually very hard. For us as humans, it's very intuitive, it's very simple, but for robots, it's very complex because you have to have like this computer vision systems. So basically cameras that take images of these this part here. And here I'll show you. So it has to identify a package, pick it up and drop it on this. And you can see there it has also to identify it, so scan it. And it has to identify which package it can pick because it has these suction cups. It cannot just pick any item. It has to be like flat and it has to pick it. And also we have to identify if there are some damages on the boxes, let's say liquid damage or something that the robot should not pick it because that should go to sideline. So those are, as humans, we can do them fast, but it's very hard for robots to do. So the vision system, where machine learning and AI comes to the rescue, is really to identify these packages. So there are multiple things. It's called item package identification and damage detection, just from images. And it has to be very fast. The images, they might not be high resolution. You might not have all the views. So there's a lot of complexity. I cannot go through the details, but just to give an example here. So I said singulation, so identifying what the package is, and also which one of these robots will take it so that it goes to the specific chute. So a lot of manipulation. So let me just move through this quickly. So, but then there is a problem. Remember, I talked about data is important, and as part of identifying this problem, the problem we had here, it's research into production. So I call it the getting the cart before the horse. So basically, in order to get this robot to be used on the field, you have to have the machine learning algorithms and models very accurate, highly accurate, because otherwise it just creates overhead and it's not really helping. But for that, you need a lot of data to train the models. So that's why I call it the carrot before the horse. And for that, how are we going to do? So the data set is small. Also, remember I talked about structured and unstructured. This data is unstructured, it's highly unstructured. It needs to be annotated. So that the model can understand what it is, like where the object is, identify what is the type of objects, etc. So for that, I'm just going to talk about actually a piece, not the annotation, but just one way to solve this problem is to create, either in lab, we collect a lot of images to mimic what we're going to see in the field, but still it's not enough because some of these algorithms we use, and I talked about deep learning algorithms, they're really good, but they're extremely data hungry. You need like 10,000s or hundreds of thousands of images that are labeled for examples. So in this case, what we did, we used synthetic data. So we generated synthetic data, and this is really using machine learning for machine learning. So synthetic data generation, in this case, I'm just going to skip through this quickly. So basically, we generated, these boxes are not true, by the way. These are computer generated. These are machine learning generated boxes. And one thing, this one is very cool because even like how they are distributed on the conveyor belt, that's very complex. So we had to use some physics-based model to simulate that drop-in on a conveyor belt. And then here also creating like labels also, so that we train another algorithm to identify from computer vision, identify the packages. There were some problems with actually, okay, we want to identify the package, but also we want to mask the address of the person because that's considered data privacy. So that's another problem we worked on. I'm not gonna go through how we solved it, but just to give examples. Another one was to identify damages. So as I mentioned, like these are damages, but these are actually computer-generated damages from existing damages of boxes, and then we superimpose them and added some randomness to them to map so that we can create a lot of scenes and images so that we can train the algorithms. This is an original synthetic data. This is a real how the image would look like. So you can see there are differences in terms of vividity. If we train on this and we show this, we will have false positives. So what we did, we used something called GANs, Generative Adversarial Networks. This is another deep learning algorithm technique to actually augment the synthetic data to look like a real image. So this is not the same, but this one, we use this as a style and we transferred it into this. And with that, I will close with actually that it's fascinating to be a machine learning scientist. There are a lot of challenges still with data, like how the data is integrated. There are missing data. Also how to marry and always keep in mind the data-driven and domain-based analysis to bring so that you don't do it in isolation. I talked about physics-based modeling and engineering to really understand how that works. Security is really important, right? We have seen now in the news a lot about data privacy and data leaking and all that. It's now with all these sensors and data that's collected and sent back and forth, malware and hackers, they're like feasting and trying to feast on that. So that's another really important aspect. It's not in my area of expertise, but I have worked with a few other colleagues on that. And as I mentioned, infrastructure now, it's really, we got with a lot of like cloud computing and all that, that's really enabled, but there's still things that can be improved. And with that, I'll stop and open it for questions.
Thank you so much, Dr. Bushra, for this informative and very, very interesting talk. All right, let's see if we have any questions from our audience. Please, should you have any questions, please write them in the comment section. Okay, so here I have a question from Dr. Rashidi. Is there any info on the average cost for building an AI, assuming data is available?
That's first of all, I want to say thanks, Dr. Rashidi. It's a pleasure to see that you're attending my talk. I feel very humbled. Your question is very interesting, like the average cost of building an AI system. I don't think there is an average cost. I think it depends on the application. I'll say like there are applications that are very simple. Like for example, for the one for GE, unfortunately, I cannot like give the numbers, but it depends on the scale, right? And I'm trying to do like the math in my head without really providing too much information that I'm not supposed to talk about, or even with Amazon. But assuming you have the data, assuming you have the infrastructure, let's say if you use AWS services, and assuming you have it becomes the brain power of the people who will build that AI system. Let's assume like you would need for an application, you might need. So now the beauty with all this automation is that instead of needing 10 machine learning scientists, which you might not have the luxury to have, you might get by 5 or even less. And then you can enable others who are not really machine learning experts to help, like software engineers and others who are a little bit more on the domain experts side. The other thing is also that's why I said it depends on the application. If the application is tailored, let's say for wind turbines, and you have like 60,000 turbines and you need to deploy it, so it's not the same thing as if you have like, let's say 300 or 1,000 turbines or more robots, right? So the deployments, the scale is key here. So I cannot give you like a very definite answer, but again, could be And I've seen like even some venture capitalists, let's say, for example, for self-driving cars like Uber or Tesla or some other companies, they spend like few $1 million to start. It's the starting point. Once you have it done, it's like definitely in the millions of dollars as investments. Once you start it and it gets going, and it's not, I'm not talking about the data, it's really building the capability. And because I also fundraised a lot and was part of programs to build some AI systems, it definitely, it's in the millions to just start. Some companies, they invested hundreds of millions even.
Okay, so let's move on to the next question. We have one from Ms. Safa. She said that in a previous talk by Dr. Kautar Maghrawi, that was our first event with the AUI Alumni Tech Talks, she mentioned that we are heading toward learning from less data. For
Yes.
AI algorithms, does that also apply to robotics?
Yes. So there are new techniques. That's why I talked about. So there are some. So deep learning algorithms was kind of like the push for that. So deep learning algorithms are really data hungry, but there are some variations now. And I can give actually a very interesting problem that I looked at recently. So like in transfer learning, for example, I have an image. Let's say I have a regular image and I want to translate it into a Picasso style or a Van Gogh style, right? So there are some algorithms called cycle GANs. They do that, but in order to do that, you need like almost like tenth of thousands of data to train on. But there are some other new, they're called neural graph algorithms that actually can take only few, like even 10, only 10 data to learn from, and then give you maybe like not the same quality, high quality of cycle GANs, but close enough. And this is really the reason why, for example, in robotics, and I did talk about that synthetic data generation. Sometimes you don't. We're even trying with that. We cannot like mimic everything that we can see, because there will be some examples we might not see. Like for example, damage packages. Every damage is unique. So we cannot see all the possible examples, but we want just to have a hint, more or less, right? And that's really, in that case, we're learning from less data, because the examples, you cannot cover all the possible examples, right? And there are some techniques to do that.
Okay, thank you. So our next question is from Ms. Rita. She first thanks you for how enthusiastic you are about your work and how you consider it fun. So her question is that, do you have to deeply understand the math behind machine learning algorithms, or get a software library to use them or something?
So it's okay. Do you want my answer or what I see in the trend? So the trend is that less people are really diving into what goes behind the scenes in the ML algorithms, because right now, if you go to GitHub, you search for an algorithm, you search you don't even know what the algorithm is search about, a solution, right? Like for example, like transfer style, right? Using deep learning, and then you get a lot of papers, and there is something called papers with code, and people put their code in there, and there are GitHub repositories where people put their code, and they have different types of licenses, especially for research. Most of the licenses, they're permissible for research. For commercial use, they're sometimes not. So, and people have been really going heavily on using software libraries and using them. However, and that become kind of like democratizing a little bit the use of machine learning, right? But really, if you want to change and manipulate the algorithm or the algorithms to what you want and and improve, you need to really understand the math behind it. Now, it's the difference. Are you a user, consumer of machine learning, or are you a contributor to machine learning? So I'll let that there.
Yeah, thank you so much. Actually, Dr. Bushra, I have a question too. I first of all really appreciate the example that you gave about how to improve reliability for wind turbine systems. And I would like to apply the same thing, but for space applications, meaning we would like to identify failure modes for small satellites.
Okay.
And you know how critical those systems can be. So my question here is how to make the satellite smarter, what are the possible challenges in implementing machine learning models?
So to make to identify failures or make the satellite smarter. So those are.
Yeah, because I would say smarter in a way, so like the satellite should be able to react fast and make decisions when faced with unexpected situations such as failures, for example.
Okay, so those are so for that. So I'll go back to one piece I talked about, right? So let me see. I'll go back to this slide because I think this is very important for you, which is understand the problem and define the problem very carefully. And the problem you have might be several problems in one, right? So
Okay.
I am a big fan of thinking system level, but solving at subsystem level.
Yeah.
Right. So the way I would advise you is to, again, divide because if you say you want to make satellite smart can mean different things. Define first what's smart. I mean, smartness can be different things. Define what smart is. What is your goal? What is your target? And if you want to say, like, for example, like the example I gave in wind turbines, make them smart is really being more proactive and instead of being reactive, right? So we want the turbines to be more resilient to failures, right?
Yes.
So for them to be more resilient to failures, which means they have to have, there's a concept, and I skipped it during my talk. It's called digital twin. So having digital twin model for each turbine that tells us what's the health of the turbine, the operating conditions, and all that stuff. But it's very unique to that. So instead of having a model that tells us on average this type of model turbine, this is how it behaves, this is very specific. So that's actually a step towards having smarter turbines, right? Because then you have really model that tells you what it is. And then in the case of failure mode identification, so you say, okay, I want to identify failures, but I want also to identify failures I don't know, right? Because we don't, and that's only part of the puzzle. Okay, so now you identify there could be failure. So what next? That's why I talked about this piece of decision making expert system.
Yes.
So you need to have an action recommendation system. There's some actually traditional, I call them machine learning algorithms, like case-based reasoners, that are very good. You can use like some actually deep learning algorithms that use knowledge-based graphs to build like knowledge-based graph and make recommendations actually like text. That provides actually recommendations for operators or recommendations that the system itself can take, right? So one thing here that I talked about is that the action either can go to a human or can go to another robot. Like in the case of robotics, I showed you the example of a robot picking up and providing to another robot and sending, right? So these are two machines in a system, so subsystem of system that work together. So there are multiple ways of thinking about what being intelligent or smart.
Yeah. Okay, let's see if we have any other questions. No, seems like that's it. So I think here we come to the end of our webinar. On behalf of AUI Alumni Tech Talk members, I would like to thank you again, Dr. Bushra, for your time and for this very, very interesting talk. And I would like to thank everyone attending this webinar. Hopefully it was beneficial to you in any way, and see you in our upcoming webinar.
I think there was another last question.
Yes, wait. Okay, so this is from Miss Nadia. I would like to know from where to start to be a data scientist, and what is the simplest way to start with?
Are you at AUI? student right now, or
no answer here. Let's
Nadia,
wait.
are you a student, or are you already, do you work somewhere? I just wanted to understand, because if you're a student, my answer will be different than if you are working. No, okay, no, you're not a student. So okay, so that means you work. Okay, already working. Perfect. Okay, so that's why I asked that. So actually, if you want to be a data scientist, there are a lot of online courses that are free. There are some that are not free, like Coursera is a good go-to place to get really educated on machine learning and the concepts. On YouTube, like I know, like MIT, they have a lot of like online classes that they make them free for everyone to watch, and you can watch them on YouTube. CMU, UC Berkeley, a lot of really, really good. Stanford, they have an excellent one on deep learning. So I would start there, but before you start really jumping directly onto deep learning, I call it like kamikaze. You just like, I think it's good to understand the concepts behind like machine learning at high level, and then you dive through some of those. And then the beauty of this is that some of these, if you take Coursera, some of the courses, actually, they do have workshops where they give you a project to do, and you have to build maybe an algorithm and solve a specific problem. So that will be my recommendation. And if you work, depending on where you work, ask them to pay for some of these, because that's benefit to them, right? So you can, there are lots of things to do, and there's definitely a big need for people in this space.
I think we have one other question here. So this is from Mr. Ayman. He said that you said that the process you involve collecting and checking the data, picking a model, analyzing, then checking the results. His question is that if the results are not what you expect, what should you do?
It's an iterative process, right? Let me go back to this. You have a hypothesis, you analyze, you validate. If it's really about it's really the scientific method, right? The scientific method. You have a problem. You formulate a hypothesis. You look at your data, your evidence, and then you go and validate. If it doesn't mean you cannot solve it. It's just you need to either change your model or maybe expand your data. And the good example I gave it for that wind turbine example, where with the data we were looking at was data from the gearbox itself, but we couldn't find anything. So we said, okay, I said, well, let's expand to the whole system. Just let's look at everything. That's how we found that actually the Estop, and we found the genealogy really was contributing to that, right? So that's how, and it's iterative. It's never stops, right? So it's iterative.
Okay. Anything else?
I think that's it.
Yes, that's all I can see here.
Okay.
Yeah. Thank you so much, Dr. Buksha. That, as I said, it was exciting to have you here with us. And,
thank you very much for inviting me.
Thank you so much. And thank you all of the attendees here. See you next time in our upcoming webinar about doing Agile versus being Agile, April 9th, actually. Yes, next Friday. Perfect. Yeah. Thank you. Bye-bye.